And so from that, Thomson concluded that the beam was composed of negatively charged particles. And the thing to realize here is the reason that Thomson is given credit was basically he kind of stepped out on the limb and said, this beam is composed of negatively charged particles, and these negatively charged particles are part of all atoms. So this was the first time that we were talking about a particle that's smaller than an atom, and a particle that is the same no matter what atom it's in. Okay, so that's kind of the significance of where we're headed with Thomson. And so they call, let's see, we'll just kind of step through. Sorry about that. I kind of talked ahead of my slides, but. All right, so now let's look at his model. And I can't remember if there's here we go. Okay, so he identified these small negatively charged particles. Okay, he didn't call them electrons, but eventually that's what they were called. And so they knew atoms were neutral by observations. And so they thought, well, if we've got these neutral particles in there, there must be some kind of positive charge that is counteracting the negative charge of the electrons. And so Thomson's theory is that we had kind of this glue or goo, that the positive charge essentially was not particle-like, that it was sort of dispersed, that the electrons were dispersed within this sort of positively charged stuff. And they call it the plum pudding model. Plum pudding is a pudding that has raisins in it. And so if you imagine pudding, the pudding is the positive charge, and the electrons are the raisins. The raisins are the negative charge that's in there. Okay, so this model held until a guy named Rutherford came along, and when he came along, we were experimenting with radioactivity. And basically, what he did was an experiment. They call it the gold foil experiment. And I'm not sure if this link is going to work for me. Let's see if I can get it to, if it'll go there, maybe. Okay, I guess in this program it's not going to let me. Oh, there it goes. All right. Okay, awesome. I like this demo here. Okay, so what he had was, I don't know if I can't write on this with this. He had a gold foil right here, and these very, very thin, like this one would be like 3 atoms thick. So these are the little gold balls. These are the gold, the nuclei of the gold foil right in here. Okay, and what he saw was that he had a radioactive source that was over here. The blue particles represent the radioactive particles, alpha particles that are being emitted. And he made several observations, all right? And so I'm going to open the slit up a little bit so we can kind of get more of an idea. And what he had around this setup was a screen that whenever one of these alpha particles impacted the screen, it would glow. And so the data for his experiment was he was basically recording the location and the number of impacts of the alpha particles on this screen. And he observed 3 things, is that most of the particles went straight through, as if they had impacted nothing. Some of the particles were deflected to the left or the right on the screen, and a few of the particles bounced back. And you can see on this every once in a while, maybe I need to open the slit a little more. But every once in a while, you'll notice that we do get an occasional one that bounces backward. Okay, all right, so let's go back to our PowerPoint now. Okay. All right, and again, here's another drawing of our gold foil experiment here, so you can kind of see it in a little more detail. All right, so here are his observations again. Most of them passed through without changing course. Some were deflected to the left or right, and a few bounced back. All right, so now what does this mean? All right, and these are kind of lined up with his observations. So these are his conclusions. One is, since most of the alpha particles passed straight through, he concluded that the gold atoms were mostly open space, empty space. And this second conclusion here, or let's drop down to this one here. Here, because a very few bounced backward, he concluded that there must be some very small dense center that every once in a while these alpha particles would hit it and it would bounce it straight back. Then the other thing he concluded was that because some of them were deflected, and the alpha particles are basically, it's a nucleus of a helium atom, which means it has a positive charge. So these positively charged alpha particles were being deflected and going to the left or to the right. And so if you can think about it, what was really happening is you've got this positively charged particle coming close to the nucleus, positive and positive, they're going to repel each other, and so that repulsion deflected the particle and changed its path to the left or to the right. And so that's where he came up with the conclusion that this nucleus, this dense center, that occasionally one of them would hit it straight on and then bounce back, that this nucleus had positively charged particles in it. Okay, so here we have Rutherford saying that our positive charge is not spread out like Thompson's plum pudding model, but it's in the center, dense center, and that most of the space is occupied by the electrons moving around outside of it. And that's where Rutherford's model stopped. He didn't postulate anything about where the electrons were and how they moved and that sort of thing. And so what we'll see is that a good bit of our development of the model from this point really revolves around the electrons and what's going on with the electrons. Okay, so that brings us to Bohr. All right, and basically what he did was start to look at what's going on with the electrons. Okay, Bohr's model, basically he said that these electrons are moving in orbits around the nucleus, and that the reason that the electrons can do this, because think about it, one of the things that people wondered was, well, if this nucleus is positive, these electrons are negatively charged, then why doesn't the nucleus just pull the electrons in? Well, one of the reasons that he said was, as long as these electrons are in specific energy levels, then they can indeed do this.